Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 2022 Nobel Prize in Physics recognized Alain Aspect, John Francis Clauser, and Anton Zeilinger for their groundbreaking experiments involving entangled photons. These experiments, conducted independently over several decades, provided conclusive evidence for the violation of Bell inequalities and laid the foundations for the burgeoning field of quantum information science. Their work addressed a long-standing debate concerning the foundations of quantum mechanics, bridging the gap between theoretical predictions and experimental verification, and paving the way for revolutionary technology. The quest to understand the fundamental nature of reality has driven scientific inquiry for centuries. Quantum mechanics, developed in the early 20th century, offered a radically different perspective from classical physics. It posited that physical properties exist in a probabilistic superposition of states until measured, leading to interpretations many found deeply unsettling. Among the most vocal critics was Albert Einstein, who, along with Boris Podolsky and Nathan Rosen, formulated the EP-La paradox in a 1935 paper. The EP-La paradox highlighted what they perceived as a fundamental incompleteness within quantum mechanics. They proposed a thought experiment involving two entangled particles, arguing that if one could predict with certainty the value of a property of one particle by measuring the other without disturbing it, then that property must have a definite value before measurement. This concept, known as local realism, asserted that physical systems possess definite properties independent of measurement and that any influence between distant objects must travel at or below the speed of light. Einstein, Podolsky, and Rosen believed that quantum mechanics' description of entangled particles implied spooky action at a distance, a concept they deemed incompatible with relativity. They argued that quantum mechanics, as then formulated, could supply a complete description of physical reality. Central to their argument was the idea that hidden variables could potentially explain the observed correlations between entangled particles, restoring determinism and locality. John Stuart Bell, a theoretical physicist at CERN, took up the challenge posed by the EP-La paradox. In 1964, he formulated a mathematical inequality, now known as Bell's inequality, which provided a crucial test to distinguish between quantum mechanics and local realism. Bell's theorem states that if local realism holds true, certain statistical correlations between measurements on entangled particles must obey a specific limit. Quantum mechanics, however, predicts that these correlations can exceed this limit. Observed violation of Bell's inequality would therefore signify that either locality or realism, or perhaps both, must be relinquished. This result was profound, transforming a philosophical debate into an experimentally testable scientific question. Bell's work forms the cornerstone of quantum foundations and is essential for grasping the significance of Aspect's, Clauser's, and Zeilinger's experiments. The inequality, expressed in its simplest form, involves calculating a correlation function S, where S must remain less than or equal to 2 if local realism prevails. Quantum mechanics predicts S can reach values as high as 2 times the square root of 2, demonstrating a clear divergence between the two frameworks. John Francis Clauser, along with his colleagues Michael Horn, Abler Shimony, and Richard Holt, made the initial experimental attempt to test Bell's inequality. In 1969, they proposed a modified version of Bell's inequality, known as the Clauser-Horn-Shimony-Holt (C+H) inequality, which was more suitable for experimental verification. This inequality helped circumvent certain technical challenges inherent in Bell's original formulation. Clauser and his team conducted experiments in 1972 using calcium atoms to generate pairs of entangled photons. By measuring the polarization of these photons at different angles, they found results that appeared to violate the CHSH inequality, a landmark result. However, their experiments suffered from certain loopholes. Most notably, their detectors were relatively inefficient, meaning they only detected a fraction of the emitted photons. This opened the possibility that the detected photons were not representative of the entire ensemble, a loophole known as the detection loophole. Despite these limitations, Clauser's experiment provided the first tantalizing experimental evidence against local realism, setting the stage for more definitive tests. These experiments were performed painstakingly, involving delicate alignments of optical components and careful characterization of photon detectors, a process that demanded significant technicals. Alain Aspect further refined the experimental tests of Bell's inequality during the early 1980s. His experiments addressed the detection loophole and, critically, the locality loophole. The locality loophole refers to the possibility that the measurement settings on the two entangled particles are somehow correlated, allowing information to pass between them. To close this loophole, Aspect implemented a system in which the polarization of the photons was chosen randomly and rapidly after they had been emitted from the source, but before they reached the detectors. This ruled out the possibility of any communication between the two measurement apparatuses that could influence the results. Aspect's team employed sophisticated acousto-optic modulators to rapidly switch the polarization settings. These modulators altered the path of the photons depending on the electrical signal applied, allowing for near instantaneous changes in the measurement basis. Aspect's experiments, conducted in 1982, provided strong evidence for the violation of Bell's inequality, essentially closing the locality loophole and offering the most compelling refutation of local realism to date. The significance of Aspect's work lies not solely in verifying quantum mechanics, but in bolstering its validity to the extent of informing the design of quantum technologies. Anton Zeilinger's work extended the exploration of quantum entanglement and its applications. His group pioneered experiments using entangled photons for quantum teleportation and quantum cryptography. Quantum teleportation, demonstrated by Zeilinger's group in 1997, involves transferring the quantum state of one particle to another distant particle using entanglement and classical communication. This does copy the original quantum state, as that would violate the laws of quantum mechanics, but rather transfers it, effectively destroying the original state at the sender's location. Quantum cryptography, in which entanglement is used to establish secure communication channels, offers the promise of unbreakable codes. Zeilinger's experiments pushed the boundaries of quantum mechanics, moving beyond fundamental tests and towards practical applications. His group was also among the first to explore entanglement involving more than two particles, opening up new avenues for quantum computation and quantum communication. One notable experiment involved creating entangled states of three photons, known as Greenberger-Horn-Zeilinger gigahertz states, which exhibit even stronger correlations than standard two-particle entangled states. These gigahertz states are highly sensitive to coherence, making their creation and manipulation a significant experimental accomplishment. The experiments of Aspect, Clauser, and Zeilinger had a profound impact on the foundations of quantum mechanics and the development of quantum information science. By providing conclusive evidence for the violation of Bell inequalities, they demonstrated that nature operates in ways that contradict our classical intuitions about locality and realism. Their findings forced physicists to confront the strange and counterintuitive aspects of quantum mechanics and inspired a deeper understanding of entanglement. The immediate impact of their work was to solidify the acceptance of quantum mechanics as a valid description of reality, even if it challenges our conventional understanding. It also spurred intense research into the potential applications of quantum phenomena, particularly in the fields of quantum computing, quantum communication, and quantum sensing. The subsequent use and evolution of their work are evident in the rapid growth of quantum information science. Quantum computing, which aims to harness the power of quantum mechanics to solve problems intractable for classical computers, relies heavily on the principles of entanglement and superposition demonstrated in their experiments. Quantum cryptography, which promises secure communication based on the laws of physics, uses entanglement to distribute cryptographic keys. Quantum sensors, which exploit the sensitivity of quantum systems to measure physical quantities with unparalleled precision, also benefit from the insights gained from their research. Specific examples include the development of quantum algorithms like Shor's algorithm for factoring large numbers and Grover's algorithm for searching unsorted databases, both of which rely on quantum superposition and entanglement. In quantum cryptography, protocols like BB84 and E91 utilize entangled photons to establish secure keys, ensuring that any eavesdropping attempts will be detected. The reception of these experiments was transformative, though did involve certain initial skepticism. While Clauser's initial results were suggestive, the loopholes raised concerns among some physicists. Aspect's experiments, with their improved experimental design and closure of the locality loophole, largely quelled these concerns. However, some physicists continued to explore alternative explanations involving subtle forms of non-locality or hidden variables. Over time, these alternative explanations have become increasingly convoluted and have failed to gain widespread acceptance. Zeilinger's work on quantum teleportation and quantum cryptography generated enormous excitement within the scientific community and beyond. These experiments demonstrated the potential of quantum mechanics to revolutionize information technology, capturing the imagination of both scientists and the general public. The direct influences on Aspect, Clauser, and Zeilinger were readily apparent in the work of their predecessors. They built upon the theoretical framework developed by Einstein, Podolsky, Rosen, and Bell, designing experiments to test their predictions. Clauser was directly influenced by Bell's theorem, Recognizing its importance for experimentally distinguishing between quantum mechanics and local realism, Aspect was inspired by Clauser's initial experiments, seeking to improve upon them and close the loopholes. Zeilinger drew upon the theoretical work of Charles Bennett, Gilles Brassard, and others who developed the concept of quantum teleportation. In turn, Aspect, Clauser, and Zeilinger have profoundly influenced numerous researchers in quantum information science. Their experiments provided the experimental foundation upon which quantum computing, quantum communication, and quantum sensing are built. Countless scientists and engineers are now working to develop quantum technologies inspired by the promise of these fields. Their work has also influenced philosophers of science, prompting renewed discussions about the nature of reality, causality, and the limits of human knowledge. Researchers such as David Deutsch, Peter Shaw, and Love Grover were directly influenced by their experimental confirmations, leading to groundbreaking theoretical advancements in quantum computing. Their influence extends to companies like Google, IBM, and Microsoft, which are investing heavily in quantum computing research and development. In conclusion, the Nobel Prize awarded to Alain Aspect, John Francis Clauser, and Anton Zeilinger recognizes their pivotal contributions to the understanding of quantum entanglement and the development of quantum information science. Their experiments resolve the long-standing debate about the foundations of quantum mechanics, providing compelling evidence against local realism. Their work has not solidified the foundations of quantum mechanics but set the stage for a new era of quantum technology with the potential to transform computation, communication, and sensing. The legacy of their work will continue to shape the future of science and technology for decades to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.